In the last video chunk, we looked at a case where k-means failed, and then our probabilistic approach, which used a mixture of Gaussians fit using the EM algorithm, that performed a lot better than the k-means algorithm. I don't want to leave you with the impression that we have a problem-free method, though, and there are certain circumstances in which our approach can fail. And so to motivate this, I want you to think about the following problem. Let's imagine we're going to kick off our EM fit algorithm again on the same data set shown in gray. And this time we're going to initialize things a bit differently. And in particular, I've moved one of the clusters here at the bottom down here to the lower part of the plot. And what I want you to spend a couple of minutes doing, pause the video and think, if we run this EM algorithm, where is it now going to converge to? And is that going to be problematic? Great, so hopefully you paused the video and had a thought about that. If not, here's the spoiler. So we're going to kick off the algorithm and we're going to run an E step to start with. And notice that instantly things look a bit, odd, in the sense that there's a single data point here which is having high probability under this cluster but relatively low probability on the other clusters, and that means the responsibility, the probability that that data point comes from that cluster of, let's say, data point n under, let's say, cluster 1, this thing is getting very, very close to 1, and there's no other data point which is assigned to this cluster with high probability at the moment. Now these guys are all getting assigned to the blue, and everything up here is either blue or purple or in between. There's nothing else which is highly red, and that means when you come to do the M step here, this single data point is going to dominate the updates for the mean and the covariance of that red cluster, cluster 1, as I've denoted it below. And so one thing to keep a particular eye on is what the variance of this cluster is doing. I'm going to look at the variance in this direction. So this is like sigma 1, 1, it's controlling this width. Keep an eye on what's happening to that as the algorithm progresses. So here's the next M step. You can see that the red cluster is leaping to be very close to that point. It's not exactly on that point at the moment because some of these points do have some probability of coming from it at the moment. Okay, let's run these things forward. Keep an eye on it. So it's starting to get a very small variance. And it's moving ever so slowly closer and closer to sitting exactly on top of that data point. These other clusters are saying, I've got all these, don't worry. We're giving all of these data points, reasonable probability mass. You're freed up, Mr. Red Cluster, cluster 1, to go and model the hell out of that data point that you've isolated from the herd. And this red one is then going to say, right, guys, I've got this one. I'm going to sit on top of it, shrink my variance down, and basically put an infinite amount of probability density on exactly the point where we're seeing that data. And boom, at this point, David Mackay called this the kaboom problem. The variance of this component here is shrinking essentially to 0. The free energy is winging up actually to positive infinity. And this does not look like a sensible way of clustering the data. So what I want us to think about now is, where's the problem? Is this just a problem with initialization? Is this a problem with the EM algorithm? Is this a problem, to do with the model? Should the model be, specified in a different way? Or is it a problem with maximum likelihood fitting? So think about this for a couple of minutes and then come back if you would. Great. Okay, so let's just talk a little bit more detail about what's happening here before we answer the problem. And if it wasn't exactly clear before, the 1D example should make this clear. So let's imagine we've got a 1D example. Our data set looks like this. We've got a bunch of points over here which are fairly close together, and we get one data point over here. And we're going to fit this with k equals to 2 clusters. If we do that, one solution might be the following. You put one Gaussian on all of these data points, and the other Gaussian gets put here with a mean equal to whatever the value of x is for this data point, and a variance which is going to tend to 0. And if you do this, you can see that the density put on this point is going to be infinite, right? Because this thing is becoming a Dirac delta in the limit. And that means the density of the overall data set, or the log density of all of the data set, which is just this thing is also going to tend to infinity. So that means that the parameter setting that we're finding here, where the variance shrinks to 0 and the mean is exactly on that data point, that is the maximum of the likelihood. It's a global maximum of the likelihood, because the likelihood takes a value infinite for this solution. So the problem is with maximum likelihood fitting, and reinitializing might help, but the only way it can help is if you're finding a local optimum of the likelihood, because this one is the global optimum. So this is actually just an instantiation of the sort of well-known property that maximum likelihood fitting can overfit. It overfits in the sense that we do not think this solution is going to be a very good prediction for held out data. We do not expect, when we see new data from the same source, to have loads of data points which are exactly found on top of this single data point, which this cluster is modeling. We expect to see data around here and maybe in the region here, but not precisely equal to the value of the data point we've seen before. So in that sense, the maximum likelihood solution is putting really high probability on the training data and very low probability on the test data, or at least lower than it should do, because it's wasting a component to model the hell out to this data point. So there are some fixes. The most logical fix, perhaps, is to go back and use a different method to do the fitting. So you could use a prior on the covariance matrix here, and that prior could rule out having very, very small settings of the diagonal elements, so it can't shrink the variances to be below a certain value. You could even use a Bayesian method to do the fitting rather than a map estimate as well, and that might alleviate these issues. Another sort of more ad hoc approach you could use is to change the model, essentially by restricting the value of the covariance matrices so the variance can't get too small. Just in the model, bake in the fact that the variances, say, can't be smaller than 0.1, or the diagonal elements of the covariance matrix can't be smaller than 0.1. That's actually needed technically to stop the free energy from blowing up. So we said in general, a system had a Lyapunov function and was guaranteed to converge if you could identify a function that was positive and bounded. In this case, the free energy is not bounded in the general case, where the variances can shrink to 0. And that's because that's easy to see, because the log density in this case is going to infinity. So the free energy can go as high as you like. And that means that the parameters are essentially diverging. So if you do restrict the values of the variances, then you end up with a bounded free energy. And then the system is sort of guaranteed to converge again. And it won't diverge. So that explains the asterisks I had on the association of the free energy as being a Lyapunov function on the EM part of the presentation. Great. So with that in mind, when you use clustering algorithms like this, you can use the mixture of Gaussian clustering, but you should check that this sort of thing hasn't happened, and you should perhaps take these mitigating steps to avoid it.